Hi guys, welcome back to In Case of Econ Struggles. Welcome to another micro struggle. Today, Maisie and I are going to talk to you about what utility functions tell you. So just a brief video where I go through some of the words that you might see in a utility maximization problem, how that translates into math, and how that math can translate into some intuition about the problem that you're trying to solve. So let's just go right into it. So let's start off with just the words risk averse. And let's think about when you see the words risk averse in a problem, particularly in a word problem, what that translates to in terms of the utility function. Well, we know that means that the first derivative of utility is positive and the second derivative of utility is negative. So I'll just add another dash there. The interpretation, we know a risk averse utility. Generally, it's locally non-satiated, it's well behaved, there's an interior solution, and for sure it's concave utility. So when you see the words risk averse, those are all the things that you should start thinking so that as you go through and start solving the problem, you have those things in mind. Now, if you see Cobb-Douglas utility, or you look at the problem, the utility function, you see that it's Cobb-Douglas. Once again, you should know that it's going to be concave if and only if alpha plus beta is less than 1. You should also know we instantly get the solution to the utility maximization problem, particularly if there's only two goods. So here's X star and here's Y star. You should instantly know that's the solution. You shouldn't even have to write down the Lagrangian. You should just be able to go right there. And a lot of professors are okay with you going straight to the solution, but again, check with your specific professor. When you hear the words, particularly this is useful for a word problem, that someone only cares about the number of things that they have, you should instantly be thinking about perfect substitutes. Again, this x and y, this a and b in front of the x and y don't have to be 1 and 1, but you should know that what we're comparing is the marginal utility of x over px to the marginal utility of y over py. If our sign goes this way, if marginal utility of x over px is greater, we buy all of x. If it's less than, we only buy y. And if it's equal, we don't care. We just want to spend all our money. Now, if, on the other hand, it says something like so-and-so needs a x's for every b y's, that is perfect complements. That's equivalent to saying this person needs to buy bundles in certain proportions of the two goods. So that's like a minimization problem. And then you want to make sure that you use that trick I taught you to deal with perfect complements, where you define a bundle as the number of x's and the number of y's in a bundle. The price is the price of the number of x's and the number of y's that you need for a bundle. You can go through and solve your maximization problem from there. So I know super short video, but hopefully just a few quick tips and tricks as you're working through some word problems for utility maximization. If this was helpful, make sure to like and subscribe, and we will see you next time for another case of Econ Struggles.